The ARM7 TDMIS is a general-purpose 32-bit microprocessor, which offers high performance and very low power consumption. The ARM architecture is based on reduced instruction set computer RISC principles, and the instruction set and related decode mechanism are much simpler than those of microprogrammed complex instruction set computers. This simplicity results in a high instruction throughput and impressive real-time interrupt response from a small and cost-effective processor core. Pipeline techniques are employed so that all parts of the processing and memory systems can operate continuously. Typically, while one instruction is being executed, its successor is being decoded, and a third instruction is being fetched from memory. The ARM7 TDMIS processor also employs a unique architectural strategy known as thumb, which makes it ideally suited to high-volume applications with memory restrictions, or applications where code density is an issue. The key idea behind thumb is that of a super-reduced instruction set. Essentially, the ARM7 TDMIS processor has two instruction sets. The standard 32-bit ARM instruction set. A 16-bit thumb instruction set. The thumb set's 16-bit instruction length allows it to approach twice the density of standard ARM code while retaining most of the ARM's performance advantage over a traditional 16-bit processor using 16-bit registers. This is possible because thumb code operates on the same 32-bit register set as ARM code. Thumb code is able to provide up to 65% of the code size of ARM, and 160% of the performance of an equivalent ARM processor connected to a 16-bit memory system. The ARM7 TDMIS processor is described in detail in the ARM7 TDMIS datasheet that can be flash memory system. Chapter 1, Introductory Information. The LPC, the 4th of February 2141, 6/8 incorporate a 32 kilobytes, 64 kilobytes, 128 kilobytes, 256 kilobytes, and 512 kilobytes flash memory system respectively. This memory may be used for both code and data storage. Programming of the flash memory may be accomplished in several ways: over the serial built-in JTAG interface, using in-system programming (ISP) and UART0, or by means of in-application programming (IAP) capabilities. The application program, using the IAP functions, may also erase and/or program the flash while the application is running, allowing a great degree of flexibility for data storage, field firmware upgrades, etc. When the LPC, the 4th of February 2141, 6/8 on-chip bootloader is used, 32 kilobytes, 64 kilobytes, 128 kilobytes, 256 kilobytes, and 500 kilobytes of flash memory is available for user code. The LPC, the 4th of February 2141, 6/8 flash memory provides minimum of 100,000 erased write cycles and 20 years of data retention. 1.8 on-chip static RAM (SRAM). On-chip static RAM (SRAM) may be used for code and/or data storage. The on-chip SRAM may be accessed as 8 bits, 16 bits, and 32 bits. The LPC, the 4th of February 2141, 6/8 provide August 16 32 KB of static RAM respectively. The LPC, the 4th of February 2141, 6/8 SRAM is designed to be accessed as a byte-addressed memory. Word and half-word accesses to the memory ignore the alignment of the address and access the naturally aligned value that is addressed, so a memory access ignores address bits 0 and 1 for word accesses, and ignores bit 0 for half-word accesses. Therefore, valid reads and writes require data accessed as half-words to originate from addresses with address line 0 being 0, addresses ending with 0, 2, 4, 6, 8, A, C, and E in hexadecimal notation, and data accessed as words to originate from addresses with address lines 0 and 1 being 0, addresses ending with 0, 4, 8, and C in hexadecimal notation. This rule applies to both off and on-chip memory usage. The SRAM controller incorporates a write-back buffer in order to prevent CPU stalls during back-to-back writes. The write-back buffer always holds the last data sent by software to the SRAM. This data is only written to the SRAM when another write is requested by software. The data is only written to the SRAM when software does another write. If a chip reset occurs, actual SRAM contents will not reflect the most recent write request, i.e. after a warm chip reset, the SRAM does not reflect the last write operation. Any software that checks SRAM contents after reset must take this into account. Two identical writes to a location guarantee that the data will be present after a reset. Alternatively, a dummy write operation before entering idle or power down mode will similarly guarantee that the last data written will be present in SRAM after a subsequent reset. Copyright Koninklijke Philips Electronic